have a hard time finding you, and I don't know if I'm speaking to somebody. So I'd rather come closer, and I wonder if you wouldn't like to come closer too. If I'm in a school classroom and I speak with students, I never to talk to them like this. Then they feel that's God who tells me the right things to learn, and that's how they fail to learn, because they try. Because I'm telling them everything, and that's the root of why, when you teach all the time, you can never do anything. I learned more about that this morning, so I'll be down here on level to be with you more. This morning I got off the bus at 10 o'clock, started over here, and thought I want to see that building with the mosaics, where I was in 1956, a tall building. Where is it? And I didn't even know the name of the building, so it was right over there. Well, so I tried to get a map, first of all, and they said, a fellow there, the information couldn't tell me. A fellow said, oh, Directoria, I'd ask there. Well, he took me part way. I finally found, it must be near here, but I found a map on the wall. But I still didn't know what to look for. So I asked somebody, Victoria, oh, that's right there. The secretary called up about 6 different people, finally said to me, go to the Institute of Geography. I think you can find one there. She said, go there and there. So I went back and looked at the map again, and I finally found it on the map. It wasn't there and there, it was way around there. So I gave that up, unless I might pass it too far. So I examined the map to see how to find the institute here, and found if I cut through here and keep it left, then more to the right of the sun afterwards, aiming toward the sun, I should get there. And I finally landed a little bit too high, but I wasn't sure whether it was or not. There was a fellow in a booth there. Anyway, here I am. But until today, I've been taken everywhere, so I learned nothing. Today, I've taken myself around, so now I have a feeling of where we are. Now I can find other things. How much better I feel. I enjoyed going by myself and using my mind to find out. So I've experienced being a pupil in school, being told everything, and I feel totally lost. I can do nothing for myself. Till the last I've done it for myself. Well, that's tonight's talk at 6 o'clock at the Central. So I'll come back to now. Well, it's also letting research come naturally. It's natural to get acquainted with where you are, explore. And that's a natural thing to do. That's how I've been learning so fast. So I finished my talk, except I might give some more examples. I'd be very happy to have questions, comments of any kind at any moment, since I have nothing to teach you. That doesn't do anything. So I'll give some samples of exploration, for example. I've given one sample of how to fail. But just a couple of days ago, I discovered if you start with the goals, then you discover what you need. If you start with problems, if you get through a problem, you don't know where the goal is still, you don't go anywhere. And I'll give some samples of that too. In fact, everything I do will probably be a sample. But I also did not take an extra hour to think over my talk this morning. This last hour was used up. And I was talking at breakfast with someone about all kinds of things. Last night I was friends here talking about this kind of a problem. But I did make a few notes. So, for example, in school, you might get the problem, what is, suppose x squared plus 3x equals 11. The student looks at that, and how do you solve that equation? Oh, it's a quadratic equation. Now, what am I supposed to do? There's a formula, which I have a hard time remembering, but is there, with a normal average, a rather weak algebra student will forget how to solve this. And think, completing the square or something like that, that's a hard time. This is an abstract statement, an abstract thing, and you're taught what to do in certain situations. You try to remember what you're supposed to do, with no feeling of anything. Can we make this into a real situation? does x squared have a picture of anything of any kind? Oh, well, it looks like the area of a square. If here is x, and this is x, then the area is x squared. Can we picture this in some way? Oh, that's 3 times x. That's a rectangle. 3 one way and x the other way. Can we put it down somewhere? Oh, yes, there's an x right there. So let's put 3 on there. So now this, so here's 3x. And the whole thing, the total area, together is 11. Well, again, for squared, I would just take the square root. But what do you do with this picture? So, well, I don't know. But when I look at it and play with it, explore. Here's a nice rectangle, and you might think, I'm more familiar with squares. Can I make this into a square? Why not try? So, well, it's much to 2, so why not put some of this up there? Oh, this distance is x. Will fit right over there. I can cut off any amount I want and put it in there. And if this isn't very much, then I can just take half of this. So suppose I take half of this. And that'll just fit up here. Now I have 1.5 x there, 1.5 x there, but it's almost a square. But the little problem, if only I can put that in, then I'd have it. Oh, but I know what that is. That's 1.5 times 1.5. So I've gotten. Now I can just take the square root. So you can discover this if you're only allowed to play with it and look at pictures of it and turn it into something real. But you're never supposed to do that. You're never given the freedom to. You're too busy listening all the time and answering questions, do problems, lots of problems for drill. You never have time to think. This is throughout first, second grade, second year in school, right on all the way into graduate school. As far as I know, it's a normal situation. Well, oh, by the way, why bother at all? If x is, let's say, 3, then 3 times 3 is 9, plus 3 times 3 is 9, that's 18. Well, that's much too big. If x is 2, and then we have 4 plus 3 and 2 is 6, 10. Oh, it's a little bit more than 2. So we can try a little bit larger than 2. Use a calculator to help quickly find a numerical answer as accurate as you want. There's no problem. You don't have to solve the equation. So even if you've found the equation at x is the square root of, for instance, perhaps your calculator has a square root button, then you push it. But suppose it doesn't. You still have to do the same kind of thing that you could have done without solving the equation. So why not see? Let's turn it into this question now. To look at the square root, for example, in geometry, suppose you have a grid here and so forth. Let's say these distances are all 1. If you draw these lines 2 crossways, let's see. Let me put them down there. Oh, look at this. There is a square here. It's a smaller square, isn't it? And this half is the same as that half, right, clearly. So this is just half of that thing. So this square has an area 1/2. So what's the distance? That must be the square root of 1/2. Or if you take one twice as big, that'll be the square root of 2. So in this original square, what's that length? That length has a distance that L squared equals 2. So L is the square root of 2. So suppose we try something for it and look at the approximation process. suppose we try, if we play around, you'll find the 1.4 is pretty close. There's a difference, 0.04, to be added on. So let's put it in the picture again. Let's draw a picture 1.4 by 1.4. This area is 1.96. So we need to be a little bit bigger. We want this area to add up to 0.04. So we now have so let's see what we need to add on. This whole thing must be 0.04. This is 1.4, 1.4. So if we add on, let's say h there, except for the corner, we have 2.8 h. Now add on that little thing h squared, and that must be equal to 0.04. And we're probably pretty close to that small, so we can find h. H is then 0.04 divided by 2.8. We really can put in minus h squared. And there's like an exact formula right here. So we can take this and divide that by this and get a pretty accurate answer. Then that, but of course that made a little bit of trouble. It's really, so let's see how much it went wrong. Now we know just about what h is, so square it, find out what h squared is very accurately. Then put that in here, we have a very high accuracy with h. And with a great speed, you find that that's square root of 2. So this kind of, Horner's method for taking square roots is a laborious thing. You learn the rules, and it'd be a terrible job to do that. But the exploration gives you such an easy way to do it. If you have a calculator with no square root button, you can go through, repeat this process a few times. You have accuracy to 10 places, and in a few moments. So it's samples of just making it real, picturing it, play around with it, then you'll see these things. And another instance, let me jump up into calculus at the moment. Suddenly dropped out of my mind. I had a whole picture of what I wanted to say now. How did I come to that? At the moment, it suddenly disappeared. So it'll come to my mind later. It'll probably come back in. So let me shift to something very elementary. All right. In the United States, they're now having national assessments of educational progress. They've had 3 in mathematics. One of their questions was subtract 298 from 313 in words. And they gave it to 9-year-olds. So you first have to, they would have to write this below that, then remember all the rules, which are rather complex. So it's so hard. So you didn't, so what percent of the 9-year-olds got the answer, do you think? Make any wild guess? Well, 17% got it. So the vast majority were not able to do this. They certainly were not thinking of how big these numbers were, Dorothy. That's clear. If they did and try to make it real somehow, they might think of a picture from 0, 100, 200, up to 300. I'm somewhere around, where is 298? 298, 299, 300. Oh, just two steps below. At that age 9, can you count from 298 and 299 to 300? They probably could by the time they were 6 years old if they never went to school. I have no doubt about that. But as soon as you go to school, then you're stopped from doing those things, and unless you stay in real life. If you also think about it outside school, which everybody does, then you have no difficulty. So if you ask those same children outside school, don't use the word subtract, that makes them think of school. You might say, how far is it from 298 to 313? 299, 100, and 13 more, that's 15. So that's 2, and 13 more is 15. So it's utterly trivial. You've got 17% answer. So in life versus in school, let me quote any of you who may be going to Guadalajara, in that on the first day, the opening day, it's a Saturday, Teresinha Cara here from Recife, Brazil, is giving a talk. I have no doubt you'll hear about what work they've been doing, the papers they've been writing, the kind of title, in life 10, in school 0. A sample is children buying fruits in the street. How much is this coconut? And that's 35. And I'd like 4. How much would that be? 3 times it is 105, and 30 is 135. It's 140. Then the same person asks the same child, what is 4 times 35? 4 times 35, think through, and they give an answer, totally wrong, totally meaningless. It's the same problem. It's happened over and over again. So that's a very striking example of which can help wake up, I hope, the professionals also, and say the whole structure of what we do simply totally kills off everybody instead of promoting their growth for the future. So if only we can make our goal growth for the future in power and responsibility of using mathematical reasoning about situations, that's how we'll all get somewhere. Now let's see. I have several interesting things. What can I tie on? I'll come back to some of these things. Or let me tell you, look at a difficult research question where the answer is not obvious, and there are no obvious tools for going at it. And playing around with physical quantities and see how they work, at one time I ran into a question: do you have a semigroup? The group operation with it's associative and commutative, but it's idempotent. X plus X equals X for all X. It's idempotent. So for example, if these are some of the elements, A times A is A, B and B is B, C times C is C, and so forth. And I thought that idempotent, this looks like the set operation. A union A equals A. Can this possibly correspond to a set of sets under union? So I started wondering about that. You might have, for example, here's A and here's B. Then C would have to be the whole thing. But suppose A were included in B, for example. In this case, we'd have to have A union B equals B. So we'd have A plus B equals B in the table. So suppose, for example, we have A plus C equals C, and then we have it both ways. Well, but here's the check. Let me start over again and suppose in this example A plus B equals B, and suppose the C is larger set still, B plus C equals C, then we would have to have A plus C equals C. Otherwise, it's impossible. Let's see if we can prove that. A plus C equals. Now how do we get down to this? Well, we have to make use of that. Can we make use of that in some way? Well, we can take A and replace it by A plus B. So A plus C equals A plus B plus C. And, with the associative law, that's A plus B plus C. Oh, and B plus C is C. So this is A plus... No. I've done something. If I used the associative law already. Well, yes, I've used it already. So A plus C equals A plus B plus C. By associative law, that's this. So we have to go from here up to there. Then this A plus B is the C plus C, and that is C. So the associative law, that is necessary. But now the problem is still, how do I invent sets to make it work? I haven't any sets yet. I just have a needed property. And I first finally got a proof way back. Then a few years later in Campinas, Brazil, I'd like to show this theorem. But I couldn't remember how to do it. But I did find it again. A few years ago, I thought, why not let the proof come more easily, more naturally? And how to do that? I felt I have to have freedom. Let my mind play around with the ideas, and then the proof ought to come. That's what I had never done. Just at least use this principle to let the time be quiet where my mind can go in any direction. Now, if the information inside me that I'm not using, it's one of the most important things in life. Of all kinds of knowledge inside you do not have in your brain. You don't have it intellectually. But if you can bring it up, you'll suddenly realize you know all kinds of things. And I've been thinking a little bit about looking at, for example, A plus B equals C as we have it here. So let's say A plus B equals C. So there's C there. And then B plus C is well, A plus B equals C. Of course, then B plus C equals B. B plus C is, I can write C as A plus B. So that's, we turn this around to get equals A plus B, which is B, and that equals C also. So from this much, you automatically have C in the rest of the places also. Anyway, in trying to think of this, I tried to picture, for example, that, for instance, here is C as a bag holding elements, but it might have A inside. You might have a B inside. So on this bag, I'll have labels. Then C, it also has A and B as labels on it, things lying inside. So with C, I have a set of things that contain it. Oh, there's a set. Can I use that set? I want to say, let our total set be the elements of G, and the subsets, the subset C will be with all those X such as X plus C equals C. That went beautifully. All the properties went through wonderfully. But then I found there's a joker. There's one that did not. Like in this case, if I look at A plus B, then C ought to be this. But how do I know that C doesn't go up like this? That includes that. Given an element there, if it's in C, then it has to be in A or in B. And so I can't have any part. That means if an element, let's say lambda, is in C, then lambda must be in A or lambda in B. In other words, this thing, I saw no way of proving that. So I thought, well, I have to let my mind be free. And a day or two later, I woke up in the morning, and I played, and my mind floated around a bit, and then it looked at this element lambda. I remember later thinking about beforehand. I thought, what does an element look? It doesn't matter what the element is at all. It makes no sense in asking what does an element look like. It had nothing to do with the question. But now in the morning, I had freedom for my mind to wander. So for some reason, I looked at this element lambda. And perhaps because I was used to picturing it as a bag with labels, I started putting labels on it. Well, lambda is an element of C. So it has to be an element of A or a B. You don't have any set of labels here. There's a restriction on what labels you have for that element. And suddenly, look, here I have a set of things with a restriction on them. So sets of labels with a certain restriction. And suddenly, well, that's when it looks at those sets. And perhaps, of course, if I could name this way, I'd just say, if that label is there, then lambda belongs to that label. And the sets are constructed. So any element must have attached to it, namely all those names of things which it belongs to. And that right away gave the whole picture. So what I do is look at the table A, B, C, D, and so forth. And for a given element lambda, I'll say it's not in A, it is in B, it is in C, it's not in D, and so forth. So there, the yes or no to this, yes or no to this. So if there are n elements here, there are n squared places, possibilities here. And just to cut out those that don't work, and then the rest satisfy all the properties. So suddenly everything would work out nicely. And in this case, there's one little tough question. How do you know when you crossed out the bad elements, you haven't lost all your elements? If you've lost them all, then all these sets are, well, the same. They're all essentially a null set. So you can't distinguish between them. Yeah, so if they're all the null set, of course the operations hold. But you need the one-to-one. And that's more tricky, but that can be done. That's not hard, really. So there's the example of freedom to come naturally. By mind waking up and floating around, doing something funny up there. But now, as I grow up again, I'm still a little child growing up gradually. Well, let's see, Tuesday, that was the day before yesterday, I took a run outside. And on my running home, my mind roamed around a little bit. I've been discovering that if you start from the goals, you can get true solutions to the problems. That's now going to be the title of my talk at Guadalajara. And I thought, why not start from the goals here? What would happen? What is the goal? The goal is to find a set of sets. Oh, well, just look at the sets. Okay, I'd hear my things. I'd hear all my elements there. And look at the sets, too, in particular the bad set C. Well, there's that bad set C. And let's see, there's A and there's B coming in also. So that they come around somewhere. Of course, it oughtn't to come out there. It ought to be inside, and so forth. And what has happened, this element, if it's not in both A and B, I have to get rid of that. So, of course, just by looking at the answer, I pretend I have the answer. Look at the answer, I see, when you take a look at it, there must be nothing up there outside A and B. That's the same statement I was making over here, the key to what to use. And I've gotten that trick by the most naturally looking at the sets, even though I didn't know what they were. And then the answer comes out, there's no more problem. that most difficult step vanishes at once. It's triviality. Just draw a picture of what you want and play with it. And gee, what a discovery that was. All these years I'd been thinking there must be some more natural way to find it out. And then just looking at the goal, where I want to be, allowing myself to look at it, it's a trivial. Which reminds me in a very elementary situation. We start so early and telling people everything. In elementary algebra, which I now often teach in lower grades, you learn how to solve, for example, Tom had number n. He had, and you have for n, and then he took n squared. Consider how to solve n squared, let's say, minus 10 equals 4n. But now we're supposed to do problem solving, and instead of just learning arithmetic or algebra, so we must put it in word form. So we say, Tom had a number, he squared it and subtracted 10, and discovered that is 4 times the number. What is your number? Then you learn what you're supposed to do to turn it into a quadratic equation and so forth. Well, why not forget all that? And we're back to the same problem as before. But first, Tom had a number. But if you don't know the number, you know how students have a hard time with letters. So you don't know what to do since you don't know what the number is. Well, why not say, oh, that's the number. So, okay, now I have the number because I have the goal, I found it. But how can you look at not only that number, but all numbers? To get the whole situation around this question. In a situation, you want to explore it, play with it, and find out all about it, as I did around here. So let's put all numbers down here. And there are all the numbers. I'll put in 0. I don't know if I want more numbers. Let's put down that number. Oh, I don't know where it is, but perhaps that number. There's a picture of that number. Oh, now we can look at it, this number squared. Of where is that? Well, I don't know, but perhaps it's here. That's what number squared. We can start putting in everything in the picture. And we take away 10. Oh, then we must take away 10. That's done. So there's my number, which has to be 4n. 4 times squared. Of course, I'm not using letter n yet, but I began to feel pretty soon after playing, it'd be nice to have a name for the number. And here you start discovering that you can work with something, put it down, and because notice now, if here's n, if here's that number, then twice the number gets here, and we're already too high. So we start correcting the picture. The more information we get a picture better. I'd go ahead. Well, that forces, if the number is there, it forces this to be higher up. And in fact, I can take 4 times this number, can't I? And here is number 4 times my number. And so this has to be above there. How much above? Oh, 10 above. So there is my my number squared. So here is the original number, and there is a number squared. And now we're back there, and we've solved the quadratic equation. We only need to take a square root. But at least, see, with the picture, again, even the essence of using a name for a number, and gradually feel I can make a squiggle to remind myself it's the same number. Then why not use letter n? And that use of so-called variable, you'll hear about the word variable, and you can't understand what variable means, and use it in various ways. It's quantity changes, it sounds like, but it's a fixed number. And if you write an equation of the variable, that's confusing, because it's not, it's a fixed number. So another sample of of looking at situations, exploring it, and you come out with answers. See if there's any. Oh, there's one. I want to get again into the university level. Oh, I think I remember what I was going to say before now, yes. And look at calculus. In calculus, you learn how you differentiate x squared and how you differentiate the square root of x. You learn also these are inverse functions. You can think of dy over dx, and the inverse would have the derivative of dx over dy. So they're reciprocals. You learn rules of all kinds of places. In particular, you learn how to do these. So, for example, to differentiate that, you look at the square root of x plus delta x minus the square root of x divided by delta x. Then, if you can remember, multiply above and below by this plus that. So you remember this thing. But why should you do that? And how to remember what the answer is? You remember the answer better without trying to remember this. It's too complex. So even memory of what the formula is hard when you learn rules where you have no feeling of what they're about. Instead of doing this, why not to take a picture of something of this sort? Oh, x squared, it looks like the area of a square, doesn't it? Haven't we heard of something like that before? So suppose we look at the area, and let's say S for the side length. What is the relation? Well, A equals S squared. Now we have, make it larger square, so it comes out here. I'm afraid I've already drawn this picture, haven't I? We have extra area. So delta A is pictured here. It's the sum of those three areas. So delta A equals twice S delta S plus S squared. So it's approximately 2S delta S. And if I'll put a dot, say approximately, if delta S is small, the plus are delta S squared, of course. So you see this relationship, and that tells you the whole story. If you want to use one of these the two things, you see what it is right away. And if you look at delta A or delta S, you have 2S. And turn it upside down, look at delta S of delta A, that's 1 over 2S. So of course it's trivial once one is the inverse of the other. But it doesn't look like that formula. I thought there was a square root sign below. Well, yes, S is the square root of A. So what happens is you're told the answers, and you're told a direct mathematical route to get at the answers, avoiding having to draw a picture. So by avoiding drawing a picture, you take away all the concept of what's going on, and you get directly at the answer in a beautifully mathematical way, but killing off the students you're teaching. Isn't that typical of all our teaching? You know it is in calculus. I know it is also in high school and all through elementary school. So of course students, by the time they come to the university, they've never thought for themselves, and you discover that even in secondary school, you try to get them to think, but they've never thought, so you give up. But they could, if they were allowed, to start practice thinking for themselves. They can become researchers. All these things are research. Now I want to, one more note. I woke up to my failure in 20 years of teaching calculus to let those students wake up. But Beth is in middle age, very intelligent woman with math anxiety all her life. I asked her a question. In a family, their smallest children want to talk about $2, $3, $4. Next children, older children, $50, $60. Old children, several $100, and so forth. Suppose if we put one there, and a million there. I guess I should have the dots here. Never mind that. What are some more numbers you might put in to cut it up into places so each child can look at this place and take a look and see other places? And she thought, well, let's see. A million there, 500,000 should be there. 200, well, if 100,000 is here, there's going to be no room for those young children. I'll have to have 10 up here. So she said, well, 10, 100, 1,000. And pretty soon, she said, well, I'll put perhaps 10, 100, 1,000, 10,000, 100,000, a million. And she just showed down on the counter, showed the places. Next she thought, okay, here is 10 with the numbers in her mind. And so, well, where'll have about 2, 3, 4, 5, and so forth. So she had 9, let's say, around here. So 11 ought to be around there. Well, with 100 there, that's impossible. So I'll have to pull the 11 down closer. So then she said, well, I'll have to pull 9 up closer too. How would we mathematicians phrase what she did when she pulled 9 up? She has to be at that interval nearly the same as that. She wants to make the first derivative continuous. Is that not so? Otherwise, different quotient here, the one thing would be very much sharper than there. So she's working with the first derivative, making it continuous. She didn't even have a function, though. There's no function there. Just has things along a line, which just happen to have a distance attached to it. And then pretty soon she thought, well, I get 2 here. With 2 there, I'll put 20 there. And I said, my heavens, what are you doing? Of course, she put 200 there. She's on her way to constructing an exponential function and has found what its derivative must be. If you multiply by 10, then it's 10 times as steep. So she's discovered that the derivative is a multiple of the function itself. So she's found the derivative of the exponential function. And clearly, if she'd gone on to make the whole thing smooth bit by bit, she'd then find, for example, she'd discover that here, of course, to add the same distance, you multiply by 10. So add this distance up here, and multiply by 2, from 1 to 2, from 10 to 10 to 20. But she'd soon see it anywhere it could come out. So she'd have 4 there, 8 there, and come out. So here's 1,000, and this of 1,024 with 10 of these steps. So dividing with 10 of them, she'd find 2 with very high accuracy. She didn't do that. If she'd gone on to, she obviously would have. If we let students play, they'll find that out soon enough. Now it gets exciting. Oh, we can get 2 accurately. How about 3? And play around with these things. You're using algebra, aren't you? You're using algebra applied to geometric distances. It's a wonderful feeling to explore. So what more beautiful thing to explore with than this? Well, here is Beth with math anxiety all her life, never studied anything but simple mathematics. She, in 20 minutes, with my asking her a question with no mathematical meaning, she constructs the exponential function and finds the derivative, with a real feeling of what the whole thing is. Now, when I was teaching calculus, if I asked the students, and as a test, write down what is the derivative, I read what they write. You won't make any sense, will they? What student will give a good description of what a derivative is? If I define an exponential function, then work out its derivative, they'll want to learn the rules that have no feeling about it. Beth, with no mathematical experience, constructs the function to find its derivative. She's beyond those calculus students. She carried on research to jump through the centuries and get way up into there, skipping all those things you're supposed to learn on the way. What is your A better example is research coming naturally than that. So now the phrase that, and that most striking way of all, for me, she had the freedom to let this research come naturally. And I think I've talked enough. So here, there's some samples I think over what it means about what we can do in life. To my mind, the key is if you can let those students be real people and use their powers. If you try to do it all at once, you might say, oh, they'd be chaos. You wouldn't learn anything. Okay, you want to keep them under control of some kind, but if the moment they get started that question of control won't be needed anymore because they're interested in school. And you can allow some freedom to explore. Teach it if you want for a while. Allow a little extra freedom too, and that can grow bit by bit and gradually spread. And in your own work, if you can't solve a problem, it's perhaps you're not familiar enough with what that whole situation is. Look for relationships with other places and see if that gives more light on your situation, other parts of mathematics or whatever. And let it'll start picking up other information you have and may start coming to you. So I think that's the keynotes that I've been learning, and I feel greatly interested by the whole thing, and I enjoy it. So thanks. But any questions, of course, if you like. Okay, I think I can respond to this. You don't have the freedom. What I hear is you can't let yourself have the freedom. And so you have to you're under pressure. So you feel trapped, you have to get out of that pressure. It may be that at certain moments, in this problem of the sets, I did not have the freedom during the day. When I woke up in the morning, I'd have a few minutes of freedom. In those few minutes, I got an idea. And then I'd wasted many hours during the day, and in 5 minutes of freedom in the morning, I could have saved. I could have skipped those several hours of study during the day. So if we are trying to solve it too much from the negative instead of from the positive and from the goal. So it's only a wasting time, and most of the time when you're trying to do things. So perhaps also drop those efforts you're making. Learn to drop them more and use more freedom during the day. It's your choice. If you feel pressure, you may not feel any freedom, but learn to sort of let yourself have a bit of freedom even if you feel pressure. And truly say, well, after lunch, I'm going to take a few moments, 2 minutes by my watch, and let my mind wander, and learn what it is to have a little bit of freedom. And I think this is human question about human people. If you practice that, if you ever do something and discover something easily, now practice that, having freedom, let your mind wander. And then you begin to get used to dropping to hard efforts when you have any sense you're not getting anywhere. And say, I'm going to take 30 seconds of silence, and throw it off your mind. That's freedom you're taking. Learn to do that more, then you'll make your efforts more worthwhile. I'm learning that still. So again, you give me a real clue to how to really get into this.
You have done very important things in mathematics.
I certainly, I know I felt a lot of freedom then to play around with ideas that look interesting. I didn't feel much pressure in my younger days. That's, I think, really the key. I think that almost anybody could have discovered the same things that I did if they had the freedom and had the same interest at that moment. And so everything I'm saying is in no sense new. We all know these things, really, but we don't let ourselves really let it come out. I had lots of freedom, and I used that freedom to look for interesting things to explore. That's the only reason that the basic reason of why I've discovered the things I did.
What about the 11th commandment? Publish or perish?
Yes, that you're under pressure. So the point is, again, I think like the same. I think in a sense we've already answered that. We feel the pressure, so it's a practice at moments to let that pressure drop. Yes. And those few moments, the practice letting our mind wander over interesting things, and we can't make a sudden change, but coming naturally will also perhaps come gradually. The publish or perish is a pressure on us, and at moments let that pressure drop and practice that, and we also start doing things. So as it starts from the goals, look at the whole situation, to picture the whole situation, make it real, and have freedom to play around with your relationships. All these things have the same kind of message. Have freedom what you would do naturally anyway. Young children, before school, of course, they're the ideal researchers. Before they ever went to school, we know that they learned, for example, how to communicate with language is extraordinary. Never being taught, those young children, how they learn all of that. The ideal of letting research come naturally. So to let ourselves get back to our preschool natural powers, which we still have. They get suppressed, that's all. So getting freedom at moments, let those natural powers come back. Well, I think the formal workshop to start, so I'd suggest that we be free as to what we want to do now. And I'll be here for if you want to chat. If you're perfectly free to get up and go. All right. I accept nobody tying you down. So if you want to stay there or come up closer, or I'll get down and walk around among you, I don't care. I appreciate it.
I think there's a catch somewhere.
Well, there are catches all over the place.
We will solve every problem, especially in Mexico. It's like
yes, that's right.
We have lots of people that wander around and
That I agree thoroughly. So, but if we stick always in problems, then we never have the freedom to find the real solutions. We get little solutions that don't help much, perhaps.